Hey guys, Mr. T here. This is another video. This one is on non-integer vertices when you're doing linear optimization. So far we've only considered simplexes that have whole number vertices, so simplexes that have corners on nice grid lines, nice whole number grid lines. So as a result, the optimal solution has so far been whole number x and y variables. Nice and easy. Obviously, that's not always going to be the case. We're going to have to deal with more difficult situations. Sometimes the solution can have decimal places or fractions of a whole. So the solution is handled differently depending on the kind of variables x and y represent. They can either be continuous variables or discrete variables. And we are looking at continuous variables in this particular video. So you're doing a set of constraints and you're drawing up a set of feasible region for certain kinds of variables, if the variables you're optimizing are continuous. So for example, they are a measurement like weight, height, volume, etc. They are variables you would measure rather than count. That's a continuous numerical variable. Then in that case, non-integer solutions have to make sense. It makes sense to have a weight that's between 160 and 161. You can have a weight of 160.5. Okay, you're not counting weight and it's not going to be whole numbers. So the solution that is not a whole number makes sense, so it'd have to be acceptable. So as a result, you will optimize as normal using my 7-step process that I've done in previous videos. But the solution is going to be at a vertex or along a boundary of the feasible region, even if the solution isn't a whole number. You're just going to find the solution and give it as is, however many decimal points it is, if it's recurring, if it's a fraction, whatever. Why is that a problem? Well, you're not going to be able to find those corners, the location, the coordinates of the corners or the vertices, when they're not sitting nicely on a grid line. It's not going to be a nice whole number. You will need to use simultaneous equations to find the vertices and not just use the neatly drawn graph. So what we're going to do is do an example where you're going to have a feasible region that doesn't sit nicely on grid lines. An example here, fertilizers X and Y have ingredients A, B, and C in the quantities shown in the table below in units per kilo. Fertilizer X costs $8 per kilo, Y costs $12 per kilo, so this is obviously going to be part of our objective function. X has 2 units of A, 5 units of B, 1 unit of C. Y contains 4 units of A, 3 units of B, and 3 units of C. So a farmer mixes these fertilizers X and Y, and that mix needs to contain at least 25 of A, 38 units of B, and 16 units of C. What combination of X and Y fertilizers should the farmer use to minimize their costs, given here? And what is that minimum cost going to be? How much would the farmer have to spend to satisfy his requirements if he used fertilizer X only, fertilizer Y only? So a few parts to this question, but the main thing we're going to focus on is part A, because the other two parts come off easy once you've done that. So showing you all the 7 steps of the process to come up, but the differences will come very soon. Here we've drawn a table to summarize all of the numbers. We've made lowercase x represent the number of kilos of fertilizer X, lowercase y represent the number of kilos of fertilizer Y. Here we've represented the number of units of the different components, A, B, and C. And then we've put in the constraints here because he needs to meet these criteria. Not be less than or equal to, they're going to be greater than or equal to those amounts and the costs we've put here. I've drawn up the constraints. Hopefully these are second nature to you now because you've been practicing. I've done the objective function because I know I need to minimize the cost. And I've also gone ahead and found the X and Y intercepts for all these constraint lines so that I don't have an hour-long video. And what I'm showing you really in this video is the new process, which is finding the vertices without using just a graph. We have to actually use algebra, simultaneous equations. So we've drawn these constraints, and you'll notice that these X and Y intercepts are not nice numbers, especially these recurring ones. However accurately you draw, you are not going to have exact placement of 0.6 recurring or 0.3 recurring or 0.6. Okay, and if you did increase your scale so much that you had, say, one grid line for every 10th, you're still not going to represent the recurring numbers nicely, and it's going to take up far too much space. You're not going to be able to draw the graph in your book. So what I've done is draw the graph as best as I can on this grid. This is sort of still the sensible size for a book or a test question. And I've written some notes here. From this graph of the simplex, you can see why drawing accurately is not going to be enough to determine the location of the vertex. It looks like the vertex might be pretty close to this 5.5 and 3.5 here, but it's not exactly. I can't be sure because I know for a fact that the intercepts are not exactly on grid lines. As the intercepts are not integer coordinates, it's not certain the placement of vertices in the graph is exact. Oh, these are exact because they're given in the intercepts anyway. This one is not. So I need to check the intersection of each constraint line with the others using simultaneous equations. Why is that? Because two lines intersect when they equal each other. The coordinates of the intersection of two lines is the solution of those two lines solved simultaneously. So the new process that I'm doing here is that I have drawn up this graph. I've recognized that there's one corner, two corners, three corners. I can easily find the intersect here. It's 0, and I just need to double check what the y-intercept is. 12.6 recurring, or 2/3. That's fine. And this one here is, this other corner here is 16, 0. So I've got two of my corners. My problem is I don't know this middle one. It looks like all of these three lines are actually crossing at the same place, but we can't be sure because this drawing is not going to be super accurate. So the process of actually finding these intersect involves simultaneous equations. So I need to find the intersection of all of these constraint lines with each other, one after the other. So I'm going to try A to B intersection. A is, the line A is 2x plus 4y equals 25. The line B is 5x plus 3y equals 38. They're my simultaneous equations. I want to know where they cross over, so I have to solve them simultaneously. So I need to use these processes that you've been done early on in the timeline, which was, I'm going to solve by elimination. Multiply the top line by 5, multiply the bottom line by -2. That will give me 10x plus 20y equals 5 times 25, 125 on the top line. Negative 10x take 6y is equal to 38 times negative 2 is going to be negative 76. I can add them together now. That's going to be 0. 20 take 6y is going to be 14y. 125 take 76 is 49. Y is going to be 49 divided by 14, 3.5. That will now let me find what the x-coordinate of the solution is. Substitute y is equal to 3.5 into 2x plus 4 lots of y. 2x plus 4 lots of y is 14 equals 25. 2x 25 take 14 is 11. X is going to be 11 divided by 2, 5.5. So we know that A and B intersect at 3. Nope, not 3.5. X coordinate first, 5.5, 3.5. That's okay. I'm done. I know where A and B cross. I need to check all of these lines, so I can't stop there. What if they intersect at different places? So I'm going to check where A and C intersect. So the equations for them, A is 2x plus 4y equals 25. C is x plus 3y equals 16. I'm going to multiply the bottom number by negative 2. That leaves me with 2x plus 4y equals 25. Negative 2x takes 6y is equal to, I think it's negative 32. I hope that's correct. I can add them together to solve by elimination. 2 take 2, 0. 4 take 6 is negative 2y. 25 take 32 is negative 7. Y is going to be negative 7 divided by negative 2 is 3, positive 3.5. That's the same as this. So if I was to substitute that into, heck, I'll substitute into the other one this time. X plus 3 lots of 3.5 is meant to be 16. X is plus 3 times 3.5. 10.5 is equal to 16. X is equal to 16. Take 10.5. 5.5. So we know A and C intersect at 5.5. 3.5. So we've got one other combination we'll check. We need to know if B and C intersect at the same place. I'm pretty sure it does, but we'll double check anyway. B, C intersection. The equation of B is 5x plus 3y equals 38. The equation of C is x plus 3y equals 16. I'm going to times the bottom one by negative 5, so we can solve by elimination. 5x plus 3y equals 38. Negative 5x take 15y is equal to, I don't know what 16 times 5 is. Negative 80. We can solve by elimination now. 0. 3 take 15. Negative 12y. 38 take 80. Negative 42. Y is going to be negative 42 divided by negative 12. Comes to 3.5. I can substitute that into any of these and I should get the answer. 5x plus 3y equals 38. 5x plus, what's 3 times by 3.5? 10.5 equals 38. 5x is equal to 38. Take 10.5, 38, take 10.5, 27.5. X is going to be 27.5 divided by 5, 5.5. So now we know that B and C also cross over at 5.5 and 3.5. So now we can proceed with our optimization techniques because we have confirmed that this vertex is actually 5.5, 3.5. Not graphically. We have done it using algebra to be sure. We don't know for certain, and actually if you look on my drawing, the intersection is happening just below and to the right of this point that we've confirmed using algebra, and that's going to happen because it's going to be too difficult to draw these intersects accurately. Okay, so now we can proceed with the rest of this question. What combo of x and y should the farmer use to minimize costs, and what is that minimum cost? Well, we need to draw our vertex and objective function table. The objective function is 8x plus 12y, 8x plus 12y. Vertex 1 was 0, 12.6 recurring. Vertex 2 was 5.5. 3.5. Vertex 3 was 16 nil. Alright, 0 times by 8 is going to be 0 plus, I'm going to do 2/3 plus 12 to make 12 and 2/3 on my calculator. Times that by 12. 152 is going to be 152. 5.5 times by 8 makes 44. 3.5 times by 12 makes 42. 42 plus 44 is going to be $86. That looks lower, so that's closer to our optimization. 16 times by 8, 128, plus 0 is going to be 128. So A, therefore, and let's just double check what the question says. What combo of X and Y should the farmer use to minimize cost? What's that minimum cost? Therefore, min cost is $86. I doubled the dollars there. With a combo of 5.5 kilograms of X and 3.5 kilograms of Y. B was two parts, B1 and B2. Let's check what they were, I don't remember them. How much would the farmer have to spend to satisfy requirements if he used fertilizer X only? Those are on our vertices. This vertex represents using X only, and it's one of the possible optimal solutions that meets the criteria. Using X only to meet constraints would require 16 kilograms of X for $128. Just double check that that's what it's asking. How much would the farmer have to spend to satisfy requirements if he used fertilizer X only? Yes, it would cost $128. And part 2 was using Y only. The only option there is the 12 and 2/3. Using Y only would require 12 and 2/3 kilograms of Y for 152 to meet his requirements. Alright, so hopefully that video shows you how we deal with non-integer vertices for continuous measurements. It is alright to have 5.5 kilograms of something and 3.5 kilograms of another thing. That is why we have to do it this way. We need to check the intersections algebraically because we cannot be sure by drawing it that this is actually where we think it is. What if it was 5? What if it was a recurring decimal here and a recurring decimal there? It wouldn't be as easy. This is actually a pretty easy example of this situation. So hopefully that helps you out, and I'll see you in the next video.